Dear students, I start with lecture 9 of 101 and 102. You know that this is Leibniz theorem U V n U n v nc1 un minus 1 v1 nc2 un minus 2 v2, and one derivation of u will decrease and one derivation of v will increase. And last term, that will be u v n. And if y equal to cos ax plus b, then this is theorem yn equal to a raised to n cos ax plus b plus n pi by 2. And we will use this theorem and also Leibniz theorem to prove this example, to find the solution of this example. If y equal to x cube cos x, then find yn. Answer. Here y equal to x cube cos x, therefore yn equal to x cube cos x plus n pi by 2. We consider u equal to cos x and v equal to x cube, means nth derivation of u and x cube as it is, plus nc1 3x square cos x plus n minus 1 pi by 2. So first derivation, one derivation less, nc2 cos n minus 2 pi by 2. One more derivation, one derivation less for case, and cos n plus nc3 3 factorial cos x plus n minus 3 pi by 2. Now we know that the derivation of 3 factorial is 0, and therefore there is no more terms in this sum. Check that. Let me explain it again. We consider u is cos x and v equal to x cube. By Leibniz theorem, nth derivation of product of u and v n means nth derivation of product of u and v is u and v, means we consider v as x cube, means v as it is, and nth derivation of cos, one less derivation, another less, one more less differentiation, and third less differentiation. This is first without differentiation, first differentiation, second differentiation, third differentiation. Now the fourth differentiation of x cube is 0, or otherwise 3 factorial is constant 6, and therefore derivation of 6 is 0, and therefore there is no term after this term. So this is equal to y cube, y equal to x cube cos x plus n pi by 2 plus 3n x square x plus n minus 1 pi by 2 plus 6 n minus 1 by 2 into x cos x plus n minus 2 pi by 2, and one more term plus 6 n minus 1 n minus 2 upon 6 cos x plus n minus 3 pi by 2. And you can do the simple calculation. Here it is 3. So yn is x cube cos x plus n pi by 2 plus 3 nx square cos x plus n minus 1 pi by 2 plus 3n n minus 1x cos x plus n minus 2 pi by 2 plus n minus 1 n minus 2 pi by 2, and this will be the final answer. There is no further simplification possible as we are not knowing about the values of x. Check that. One more sum on the board. Find x raised to p log x n where p is greater than n. Again I remind you the Leibniz theorem UVN, that is u and v, one less derivation of u and one more derivation of v, another one less differentiation of u and one more differentiation of v, and lastly it is u and v. And we have two formulas, y equal to ax plus b raised to m, yn equal to m factorial, m minus n factorial, a raised to n, ax plus b raised to m minus n. This is the first theorem. And if y equal to log ax plus b, then yn equal to minus 1 raised to n minus 1, n minus 1 factorial, a raised to n, ax plus b raised to n. This is one note in the second. This is first theorem, and this is one note in the second. As I am writing 21 here, you will find it on the second. Answer here, y equal to x raised to p log x. Therefore, yn equal to p factorial t minus n factorial x raised to t minus n into log x. You can see that it is x raised to p, means it is p factorial p minus n factorial, value of a is 1, so it has no meaning, and therefore it is m minus n here, and log x as it is. Then one less derivation plus nc1 p factorial p minus n plus 1 derivation and one differentiation of log x is 1 upon x. Plus nc2 p factorial p minus n plus 2 factorial x raised to n minus p minus n plus 2 and differentiation of log x is 1 upon x, and now 1 upon x2 minus 1 upon x square. Likewise other terms, and the last term is NCn x raised to p as it is, and the nth derivation of log x is minus 1 raised to n minus 1 n minus 1 factorial upon x raised to n. So we are taking this is equal to p factorial and log x upon p minus n factorial plus NC1 1 upon p minus n plus 1 factorial minus NC2 p minus n plus 2 factorial up to minus 1 raised to n upon n minus 1 factorial p factorial. So this will be the solution. Here students, one more sum on the board. Leibniz theorem and two another form are also on the board. Here y equal to log x upon x, that is 1 upon x into log x. So we have two functions, 1 upon ax plus b, then yn is minus 1 raised to n factorial a raised to n, ax plus b raised to n plus 1. You can find this formula as I am writing it in 22 here. You can find it on the 2. And y is equal to log ax plus b, yn is equal to this. Also it is number 2. This is Leibniz theorem. Therefore, this this is two function log x upon x means 1 upon x into log x, and therefore yn is equal to log x as it is minus 1 raised to n factorial x raised to n. NC1 1 upon x minus 1 raised to n minus 1 n minus 1 factorial. Here it is n plus 1. Here it is x raised to n. One more place. NC2 minus 1 upon x square minus 1 raised to n minus 2 n minus 2 factorial x raised to n minus 1. And other terms plus minus 1 raised to n minus 1 n minus 1 factorial. This is nth derivation of log x x raised to n and 1 upon x as it is. Value of NCn is 1. So throughout this is minus 1 raised to n factorial upon x raised to n plus 1. X raised to n is in common. So what we have, if we take, can we take n plus 1? Yes, I think we can take n plus 1. Okay, n plus 1 is in common. So what we have, that is log x. This NC1 is n. We use it here and therefore n factorial is common. Minus 1 minus 1 by 2 minus 1 upon n. See here, minus sign is there, means it is n raised to n minus 1, and we use 1 minus sign it there, and therefore it is minus sign is twice, and therefore if we multiply any term by minus 1 square, then value will remain unchanged, because minus 1 square is 1. See that? Therefore, this is equal to minus 1 raised to n factorial and this will be the final answer. See here, NC1 is n, you should know, NC1 is n, NC2 is n minus 1 upon 2 factorial or 2, NC3 is n minus 1, n minus 2 into 3 factorial or 6. NC4 in denominator it will be 4 factorial, and one term n minus 3 will be increased in n minus 4. NC4. I think you understand this, but this is the first lecture of Leibniz theorem. sums on the Leibniz theorem. Actually this is 9th lecture, but the sums of Leibniz theorem just begin, and therefore I give you suggestion that you have to do lots of practice of the previous sum. With this note, I stop this lecture here. See you in the next lecture. Thank you very much.